Hey, what's up guys, my name is Cherno. Welcome back to the Game Engine series. We are back and we are going to be doing a little bit of a different format. So let me know what your thoughts are below as we get into this, because I've just slowly been realizing that the way that the Game Engine series is going at the moment, it's very kind of detailed. It's very like me writing code in front of you guys, which is just not going to scale well as we get into more complex features in the engine. And the way that I see things, at least for myself, I have to make decisions. This isn't like some company. This isn't like a team of people behind this. It's just me making this series. And I need to kind of, make sure that I've got time for other things, such as, the actual development of Hazel, like Hazel Dev and all of that stuff, actually making a proper game engine, being able to make a game with it, hopefully. And I feel like the way that we're moving along with the Game Engine series is just a little bit too slow. So I've decided to change things up a bit. I did put up a video, there'll be a link up there, regarding like what's going on with the Game Engine series in general, and we are basically going to be following that course. So what I've done is I've actually already worked on some features, which we'll talk about now. They're already integrated. I'm about to push them to GitHub, and I'm going to just walk you through the work that I've already done instead of you watching me do all of the work. Now, I'm going to try my best to make this as detailed as possible. We're basically moving from line by line tutorial series style videos to devlogs, postmortems, but very in-depth ones, not like the Hazel Dev ones where I just show you guys the features, talk about my story, my journey, all of that. I'll do that as well, but this will be we will walk through the code. I'll show you some things that I learned along the way, that kind of stuff, and also hopefully give you some insights into decisions that were made. However, if you want to actually see every line of code being written, every decision being made, you can do that because I've streamed everything that I've done here on twitch.tv/thecherno. There'll be a link in the description to that live stream. I'm making the video on the videos, the VODs, public for everyone, right? They used to be only for Twitch subscribers. As of right now, I need to actually flick the switch, but before this video goes up, I'm going to change it to public. So if it's been within 60 days, because Twitch only keeps them for 60 days, you can actually watch all of the VODs if you want that. You'll have to I've labeled them mostly Game Engine series if they're about the Game Engine series and not about other stuff that I stream, like just Hazel Dev kind of development, that kind of stuff. So it should be fairly easy to find, hopefully. Past 60 days though, I do upload them to Patreon. To YouTube and give access to patrons. So there'll be a link in the description as well, patreon.com/thecherno. Best way to help support, my series and everything that I'm doing here. And you'll also get access to those kind of past live streams forever. They're not going to expire because they're uploaded to YouTube. So that's basically the scope of things. But anyway, let's stop talking. Let's dive into the code. I'll show you guys what's new and what's changed. So first of all, actually, let's talk a little bit about where we left off last time. I think we were doing mouse picking stuff and that had pretty much finished. And the next stage was really working on the material system. Now, I just want to say that a material system is kind of something that applies a lot more to a 3D engine. This, Hazel is a 3D engine. The way I see it is, it is a 3D engine. At the moment, we're kind of doing 2D rendering. I mean, it's still kind of in 3D space, but we're trying to keep it two-dimensional, even though our rotations and everything are very much 3D, I think, at the moment, and we've got a 3D camera. But the point is, we're focusing on 2D rendering and a full 2D workflow. That's kind of our goal, but we still need the system, the underlying system, to be 3D, right? As in, it needs to support a 3D workflow. And the way that we typically render things is by using materials. If you're not sure what a material is and how it needs to exist and all that, there's a video up there. I did talk about this, and it was kind of like a Game Engine series episode, although it was a live stream. You can take a look at that video and see how what materials are and all of that. But basically, in order to support a material system, we need a better shader system, because materials are basically shaders and a bunch of data as well to go along with that. So what I've done is I've basically changed the whole way that we deal with shaders. So let's take a look at that. So basically, if I launch this just to be, just to show that this actually works, and of course it's recompiling stuff. I don't know why. Anyway, if I open up pinkcube.hazel, you can see that everything is basically exactly the same as it used to be. Nothing has changed since the last episode. We can still click on stuff, obviously, and pick stuff, but the underlying shader system has changed entirely, and that's what we're going to walk through. Now, I do have diffs here, Like if we look through all of this, this is what's changed. As I mentioned, I haven't committed anything. This is going to go right into the master branch, but I haven't committed anything. So we can actually walk through these diffs. In future episodes where maybe I do actually commit from time to time, we can go through like, you know, the commit log basically and see everything. That'll be okay, but I'll just more or less share the code. If you really want to see the diff, you know, you can go to a particular commit and view it. There's actually a question I get pretty often is like, how do I view, you know, this particular episode or whatever? If you actually go to GitHub, you know, there's this kind of 217 commits over here, right? You can click on this and then it will actually take you to all of these things. So for any of these, you can just click on this hash here and actually view the diff of everything that's changed, but you can also browse the repository at a particular point in history. So I can go back to like literally like, you know, the first episode or whatever. I don't know if I'll go back that far because that's a while. But if I go back to like, I don't know, somewhere like here, dispatching events from GLSL, I can click this browse repository button and you can see this is the repository from that point in time. So like, you know, Sandbox probably looks very bare bones. Yeah, that's it, right? There is no hazelnut application. So you can actually, you know, you can check that out if you have it checked out locally, just like in fork, right click, check out commit, you know, or you can do it through the command line, or if you're just browsing it through GitHub, you can also do that. So there's always a way for you to recall a particular episode or like whatever changes happened. So I don't think I'll go through the diffs exactly. I might skim through them, but basically I'll just talk about what's changed and you know, what the, I guess, decisions, why they were made and what the journey was like, all of that kind of stuff. But as I mentioned, because this is kind of a new format, let me know what your feedback is. But I'm just going to tell you guys straight right now, there is no way we can continue writing code line by line. Like that's just not going to happen. We're not going to make an engine that way. I think that you know, the videos that are helpful to people who are very much beginners and want to write code line by line, I feel like we've done all that. You know, I feel like we've moved past that. You should now be able to watch a video like this and understand how a system works and implement it yourself. That is my goal. That is what I think should happen. And I'm going to try my best to make that happen for you guys. I promise. So, yeah, so what's happened then? So the way that shaders used to work is we simply used to load them like from a file and they got immediately sent into like, I don't know, into OpenGL shader compiler basically. The way that they work now is very much the same. If we open up Renderer 2D and we take a look at the way that we load like this, we really only have one shader at the moment, right? Texture.glsl. So if we look at assets, you know, shaders, texture.glsl, this is the texture. Sorry, this is the shader. So what I've done first and foremost is I've actually rewritten it. I've rewritten it very slightly. So and actually, this is where the diff might be useful. So if we look at the diff, what has changed? So the biggest thing that's changed is we no longer will ever use plain kind of uniforms. The reason being, one of the big changes that we want going forward is we want to be able to support Vulkan as a rendering API. Now, at the moment, and for the, you know, unforeseeable future, we're going to continue just doing OpenGL. Hazel Dev at this point in time supports Vulkan. I'll leave a video up there that you can check out if you want to see where Hazel Dev is at and what that's like and my kind of Vulkan journey. I recommend all of you guys actually watch those Hazel Dev logs because they can be extremely useful to see the bigger picture of engines and like how we actually, you know, do maybe more advanced stuff. Because I know some people are kind of, you know, wanting to move past the stuff that we're doing here that's kind of shown very verbosely, I guess, in a very detailed fashion. But basically, because we want to support Vulkan going forward, you know, we need to be able to support OpenGL now because that's a decision I've made. And so we need to basically kind of support both. But I don't want to do things in a strictly OpenGL only fashion because if I do that, then it will kind of lock us into OpenGL for a lot longer than we need to be, and then it'll be harder to rewrite things. I'm kind of looking ahead a little bit more. And so because of that, because we need Vulkan, Vulkan also uses GLSL. However, a common misconception is that it's the same as OpenGL's GLSL. It is not. It is different. There are things in Vulkan that don't exist in OpenGL, and there are things in OpenGL that don't exist in Vulkan. And I mean in specifically the shading languages, right? A good example is uniforms. Uniforms do not work in Vulkan. It's not a thing. You cannot just say uniform, you know, mat for transform or whatever. I don't know why you have that in your fragment shader. I mean, I guess it can be useful, but anyway, you know, you don't have this in Vulkan. It doesn't exist. It doesn't matter if you have a layout location for it, whatever. It does not exist, right? In Vulkan, things need to be either as a push constant, which looks like this, layout push constant, and then it's basically a uniform buffer, right? So you have like uniform transform, and then you have mat for, transform or whatever inside this kind of buffer. And you probably, would give it like a layout and all of that kind of stuff. Or you have it as an actual uniform buffer, which looks like this, which looks very similar as well. Let's not compile that, which just basically, instead of push constant, it just has like a particular binding, right? That's how uniforms work in Vulkan. There are no uniforms. There are uniform buffers, there are dynamic uniform buffers, and there are push constants. That is how, and there are like storage buffers. We won't talk about some other more advanced things because they're not really, like I'm talking about the simple case of how do I get a matrix, how do I get a vector from my CPU to my GPU and then access it in the shader. And this is the answer, right? So because of that, we need to get rid of uniforms. Now, in the case of this, I mean, what do we have here before? We had a view projection. Now, the thing is, this, you have to realize the context of this shader. This is not a 3D model kind of shader. This is not our like PBR shader that we render our scene with. We're dealing with a 2D renderer. So this shader, technically speaking, will more or less run once, right? What do I mean by run once? I don't actually mean run once. I mean, like, this is more or less going to be like one draw call, maybe 2 draw calls, right? If we have like 10,000, I don't know what the limit is, but basically we can render like a lot of sprites at once, right? In a single draw call. That's the purpose of this batch renderer, 20,000 quads. So in our pink cube scene where we're rendering 3 quads, that's a single draw call, right? So it's not a huge impact here, but when we have a 3D scene, every single object, every single submesh, most likely, unless it's batched together, will be a separate draw call. We could easily have over 1,000 draw calls. Now, something like the view projection matrix, that's the camera. That does not change over any of those 1,000 draw calls in a single render pass. Let's just pretend that we're just rendering our render pass from the point of view of the camera. Here are all of the objects in our scene. That does not change, right? And so because that doesn't change, why would we need to, and this is the big thing though, out of those 1,000 objects, it's very, very common for us to have different materials, right? Different materials have potentially different shaders, right? So instead of us having to have a view projection matrix that we set per shader as a uniform, right? Because usually shaders have their own kind of uniform storage. Again, this doesn't exist in Vulkan, but we have our own kind of uniform storage per shader, right? Instead of us having to update all of the shaders in our entire engine, what we can do instead is we can use something called the uniform buffer, which is basically just a way for us to be like, hey, GPU, allocate a block of memory for me that is accessible by shaders, right? That's what a uniform buffer is. It's a buffer of memory, which we can then let shaders access. So I can say that, hey, I want to create a uniform buffer at index 0, right? It's going to be my camera buffer. And then if shaders want, they can be like, hey, hook me up, man. I want that binding 0. I want that camera buffer. I need it because I need to render this from the point of view of the camera, right? That's how uniform buffers work. The good thing about them is that they're global across it's a GPU thing. It's not a shader thing, really. I mean, it's intended to be used by shaders, but it's not like a per shader situation. No, it's just a buffer of memory on the GPU that we can then use inside any shader we want. And again, because something at binding 0, it's not like a per shader thing, it's global. It's across all of our shaders. Any shader in our whole engine can be like binding 0, uniform buffer, hook me up. I want the camera view projection matrix, and it will get it, right? So what that means is that now suddenly this is entirely separate from shaders. Right? This camera stuff is not something that we need to worry about on a shader level. It's something that we worry about on a renderer level. So the renderer at the beginning of the frame can be like, hey man, set up my camera. And as I mentioned, we switched to using uniform buffers. So what does that look like in code? We have a uniform buffer class, which we will explore in a minute. I think I'll save that for another episode because I noticed that I'm already going pretty in-depth. As I mentioned, it's a devlog, but it's super in-depth. So let me know what you guys think of this because I do still want to actually, teach this stuff. I don't want to just be like, hey, this is what I've done. Let's move on. That's boring, right? So we might actually explicitly look at how uniform buffers work in a separate episode, but today we'll focus on like the shader stuff. So we create the uniform buffer, and then you can see that in begin scene, That's our job. Like, we know the view projection matrix, the camera and the inverse of the transform, or in this case, it's actually just the camera's view projection matrix. Then we can just set that data onto the GPU. And that's it, right? We do this once per frame when we start a scene. Why? Because starting a scene is basically analog to setting a camera, right? There's no, we don't have like environments, so we don't have anything like, special like lighting setups. We just have a camera and we render our 2D geometry from the point of view of the camera. So starting a scene is providing a camera, setting all of that stuff up. That's what we're doing. And then we start the batch. And then now our shaders can just be like, uniform camera, it's at binding 0. I want access to that view projection matrix. You can give this a name, like, camera buffer or whatever, and then view projection. That might even be better. I don't know why I've just written it like this for now, which basically, if you don't give it a name, you just access it as if it's a normal uniform. But as you can see, that's what we do. So it works very similarly to what we had before. Before, we literally just had this, right? But it means that this is something we need to set this uniform for every shader that uses it. If we had a slightly different shader that did something else, we'd also have to give it this, and we'd also have to set it, right? And obviously the way that we can set uniforms is by either binding the shader by doing GL use program, and then doing GL, uniform mat matrix for FV, for the matrix and setting it, or we can actually just cut out the binding and do GL program uniform matrix for FV, provide the shader ID, so the program ID that OpenGL gives us when we create the shader, and then actually upload that matrix per shader. We don't have to do that anymore. We just say that our shader is hooked up to that uniform buffer. Done. So that's all that's really changed. And again, the reason this change exists, if we were just doing OpenGL, I'd still make this change. That's what uniform buffers are for. It's for data that you share across shaders, such as like camera, environment, maybe shadow information, whatever. Stuff that basically is not particular to a particular shader. Particular to a particular shader, right? So a camera is a good example, because we want to render our whole scene from the point of view of the camera. It doesn't matter what material, what shader is being used. We still need to know where the camera is. So that's perfect. Now, the other stuff that's really changed here mostly has just been like, this stuff. So for example, with this sampler 2D, we've been explicit with our binding. Right now, bindings for textures, there are 32 of these here, but bindings for textures work, and again, I don't think I'll spend too long talking about this today, but basically, if you have a sampler 2D, let's just ignore the array for now. I have like some kind of texture that I want to set, right? In OpenGL, it's possible for us to just do uniform sampler 2D, and then we have to set that texture to be like a value. So we do GL uniform 1i, we set the sampler to be like 0, and by doing that, it means that we can do GL, GL bind texture unit, or GL active texture if we're really old school, and set it to like be, 0 is the active texture, and then I'm binding my texture. In more modern versions of OpenGL, and in Vulkan especially, in Vulkan it's required, but in more modern versions of OpenGL and GLSL, it's optional. You can actually just write code like this. So what that means is that I'm setting the texture unit to be 0. No more GL uniform 1i, none of that, right? This is texture 0. Right? Now I think you can override it by setting uniform 1i if you really want to. I'm not 100% sure if that even works. But my point is, you can actually just in your shader just define any texture unit for this right here in the GLSL code, which is great. And in Vulkan, I think in Vulkan it's mandatory that you do that. There's no such thing as setting integers in the shader to be like texture units or whatever in Vulkan. It doesn't exist, right? So we have to do it this way. Also, everything else has to be hooked up with certain locations. So for example, we have an vertex output. I've put this into a struct. We've set it at location 0. We can't just say out and then match it by name. It gets matched by location. So what that means, by the way, is that you'll notice here that we jump from 0 to 4, right? And the reason we do that is because I think it's every 16 bytes occupies a slot in this location, right? So vec4 16 bytes, and this is another, maybe it's every 8 bytes, because that's 16 bytes, and then this is 16 bytes. Maybe it's just because of the padding. I'm not 100% sure. This might be 16 bytes, that might be 8 bytes with 8 bytes of padding, that might be 4 bytes with 12 bytes of padding, and then another one. But the point is this needs to be at location 4, right? Because we have apparently for, you know, either, I don't know, again, as I said, per 8 bytes, per 16 bytes, I'd have to double check the documentation, but that's basically what we do. So this isn't like per struct or whatever, it's dependent on the size. And then obviously for this flat int or whatever, because we want it flat, we can't really put it into the struct, we have to have it outside of the struct. I'm not sure if it's necessary to have it as flat. Yeah, it's probably not. I think someone may have done that in a pull request, I'm not sure. I've left it as flat for now, because it shouldn't change across vertex shade, across vertices, because it's going to be the same object. It'll always have the same entity ID. So I don't think it's going to interpolate over it. I mean, it might try, and maybe that's what flat does, prevents it from trying in this case, because even if it did interpolate, it would wind up with the exact same value, because the entity ID is going to be constant across all of these vertices. But anyway, so the point is we have to include these locations. Yeah, I think everything else we basically had the same, right? So again, referring to this, nothing else really changed. It's just we put this stuff into a struct now. We gave it a location because everything needs to have like a binding or a location. And that looks pretty good to me. So that's basically, we can just mark that as done. So that is basically the shader changes that have been made. To the actual shader. So as I mentioned, we're now compiling Vulkan shaders. So what on earth does that look like in the pipeline? How does it work? So instead of grabbing this text and sending it to OpenGL into like GL, I don't even know what it is, GL shader source or whatever the function is, right? We don't do that anymore. Instead, we use something called SPIR-V. Now, SPIR-V is a shader compiler. It compiles into this kind of intermediate byte code, right? So what I want to do is just show this, right? You might want to look at this. You will want to look at this if you've never heard of SPIR-V before, but it's basically it's like this whole like shader ecosystem, I guess. That's a nice way of putting it. So it's okay, standard portable intermediate representation. It's basically like a shader. It's like some intermediate shader representation, right? And then what you can do with this kind of shader code is you can do a lot using the tools that SPIR-V provides you with, or you can just flat out be like, the SPIR-V bytecode, I'm going to give it to OpenGL, right? So basically the pipeline looks like this. You grab this text, you compile it with SPIR-V, right? We're using shader C in this case, which is like a Google shader compiler, I think. That seems to be what everyone's using. So we're using this library, shader C, to actually compile it into SPIR-V. And then we're using a few of the Cherno provided SPIR-V libraries to actually reflect on that shader code, meaning we can actually, once we compile this to that byte code, which is literally just binary, just a bunch of bytes, right? It's almost like when you compile C++ into like a translation unit and it becomes like a .object file, a .obj file, or whatever, kind of like that, right? It's a little bit more high level though, I think, than like machine instructions. But basically, once you have it in that format, you can reflect on it, meaning I can pull out information about like, you know, what uniforms does it have? What uniform buffers, like what uniform buffers do we have? Do we have any push constants? I haven't talked about push constants, but I probably won't for now because we're not using them. Oh no, I did talk about push constants loosely. You know, what textures do we have? What resources do we have available to us inside the shader? We can reflect on it, which is fantastic from a validation point of view because we can make sure that we have everything we need. And for certain things like, you know, push constants as an example, because that's usually where we would want to have our material kind of uniforms, right? Our material properties, material, you know, variables, whatever. We can actually ask it, what do you have available? How many bytes does it take up? What are they called? Stuff like that. And then we can create a material system around that, which is what Hazel Dev does. So that's fantastic. But then also we have the ability, once it's in that SPIR-V format, to cross-compile it to anything else. I can take this code, compile it with SPIR-V into the SPIR-V binary, right? Then I can cross-compile it into Metal, the Metal shading language, or into HLSL, DirectX shading language, right? Or into, you know, in this case, we're actually using that to convert it into an OpenGL compatible GLSL. So as I mentioned, this is Vulkan GLSL, right? I mean, at the moment, this should work in OpenGL, but as soon as I start introducing things like push constants, so if I have a little push constant here called transform maybe, and it actually does contain my transform, right, what will happen here? Well, this is not OpenGL GLSL. What's a push constant, right? It doesn't work. But what we can do is we can still compile this into Vulkan GLSL, to Vulkan SPIR-V, then take that Vulkan SPIR-V binary and open it up in like SPIR-V cross, which is the cross compiler, and tell it compile it for OpenGL. And what it will actually do is generate GLSL text that we can read. It'll look like this, that will now be compatible with OpenGL, right? And then we can send that into SPIR-V again if we wanted to, get a SPIR-V binary, and then just do GL shader binary to send that binary to OpenGL. Or we could take the text directly and put it into OpenGL, right? Just the same way we were doing before, which is just reading text and putting it into OpenGL, right? Telling it that this is my shader source code, please compile it for me. But it's better to do it with SPIR-V because you'll actually, apart from getting more metadata and more information if you need it, you can easily cache that onto disk. And then you can read that cache, right, at any point, instead of having to go through this process again. So basically, once you've decided this is my shader, I'll compile it, you can write that binary result, the binary shader, to disk, and then never look at the source code again. And you can ship that if you want, because the shaders might not change. It might change if you have like dynamic shader compilation, and maybe stuff depends on, you know, whatever. But if you have those binaries, that's it. And it'll be way faster because it's not going to have to look through this code and compile it, do anything. You're not going to have to open or read text files, right? It's going to be in that format. You can give it to, you know, GL shader binary, and then you're good. So basically, that's how this works. That's how the Hazel pipeline works. We take Vulkan GLSL code, we compile it using SPIR-V into a binary file. We then take that binary file, that Vulkan compatible binary file, we feed it into the SPIR-V cross compiler. That gives us an OpenGL compatible GLSL text file, or just a string. We take that string, we compile it using SPIR-V, but this time for OpenGL, and then we cache both of those binaries to disk. And we can now give that to OpenGL using GL shader binary. One step that I missed there was the reflection step. Because SPIR-V is kind of made for Vulkan, we actually can't, okay, so in this scenario, let's talk about this. So what does this actually become in OpenGL if push constants are not supported? Well, what it will actually do is, first of all, we can give our push constant our name, right? So that could be like uTransform or uRenderer uniforms or whatever transform, right? Let's just pretend it's that, and we can access it, as you would here. Maybe if you were rendering a 3D model, you'd multiply it with like, this as an example. We can actually take this, right? Or what SPIR-V cross rather will do is it will take this and it'll be like, okay, so what I'm going to do is I'm going to make a struct for you. I'm going to call the struct transform, right? And then I'm going to add your little transform into the struct, right? And then I'm going to make a uniform transform uRenderer uniforms. So basically this becomes that. It just becomes a plain old uniform, but it's a struct, which is obviously fine and valid GLSL, right? So that's what the SPIR-V cross compiler will do with push constants. Now, can we then ask the shader via reflection, tell me what your uniform is? OpenGL actually has its own reflection functions, but we're trying not to use them because, again, trying not to stay in the OpenGL ecosystem too much. But can we do that with SPIR-V reflect? The answer is no. We can't look at these uniforms. Why? Well, they don't really exist in Vulkan. Not really worth, I guess, support. I don't know why they didn't support them, but they didn't. What we can do, though, is we can inquire about push constants. So the way that this actually works is, even though we're using OpenGL, we're compiling using Vulkan. We're compiling Vulkan GLSL into a Vulkan SPIR-V binary, and then we're taking that SPIR-V binary and reflecting on it. So even though we're then later cross-compiling it into GLSL, into OpenGL GLSL, and then using that in OpenGL. So we still need that Vulkan binary. We still have to have it so that we can reflect on it and find out information about, like, oh, you have a push constant, which for OpenGL we know becomes this, right? But you can see the naming is the same. uRenderer.transform, uRenderUniforms.transform. It works obviously for both shading languages. Okay, so does that also mean then that if we have Vulkan, there's another stage to this. I don't think we'll get into this too much, but basically, another thing that we do in Hazel Dev is, and see, this is why it's so useful. You know, I love the Hazel Dev project because apart from that being kind of me making my own engine without like, you know, having to like teach it every step of the way and thus not getting very far, apart from that, it's also really useful for this series because obviously now I have a much more detailed idea of the bigger picture. So because this is a good example. There are some cases in OpenGL, there are some cases in your GLSL code where the actual physical GLSL code might have to be different between OpenGL and Vulkan, right? So I'm talking about like calculations. So it might be desirable for us to do something like, if instead of running two different shaders, which we never want to do, that's why we do this whole thing, by the way. We want to support OpenGL and Vulkan, and maybe DirectX in the future, maybe Metal in the future, who knows? But we don't want to write our shaders multiple times. So what we do instead is we write it in one format, such as Vulkan GLSL, which I'll admit is not, I would probably choose HLSL if I had to choose a format, but since we don't have any plans at all for supporting DirectX like ever, you know, because the only reason we'd need to is if we wanted to ship on like Xbox, which I don't think we're going to do anytime soon at least. And if we do I don't know, we can add it. We can always add it. But anyway, and so it doesn't make too much sense for me to use HLSL if we're never supporting DirectX. So basically, what I was saying was that with this Vulkan GLS, with Vulkan, it might be with the whole Vulkan / OpenGL thing, it might, I don't know why I started this conversation, but basically it might be desirable for us to actually, you know, instead of writing our shaders twice, once for OpenGL, once for Vulkan, if the actual content, like the calculations have to be different, we can use preprocessor like arguments, you know, directives instead. So we can actually write a little thing such as like int, you know, value equals 0, float value equals 0, and then if OpenGL maybe value, maybe we normalize it or like we put it into a different range, you know, so we say something like this, value equals value times 0.5 plus 0.5, you know, just for OpenGL, or something, I don't know, I'm making stuff up, but the point is we can easily do this using preprocessor directives, but that means that when we compile our Vulkan code, we actually need to compile it with this flag, because obviously, you know, when we cross compile it, since it's using that SPIR-V binary, this stuff will have already been evaluated. So basically what I'm saying is that we can't simply take the Vulkan SPIR-V and then feed it into the cross compiler. From the beginning of the pipeline, from the text, we need to be like, this is an OpenGL Vulkan SPIR-V binary. So that actually does have a bit of an effect on the way that we like cache these binary files and all of that stuff. A real world example of this, by the way, is Vulkan actually has a different depth range. OpenGL has -1 to 1 for its like depth. Vulkan has 0 to 1. What that means is that for some calculations, you know, when, for example, we do like shadows and we have to, you know, calculate the right, you know, once we look up the shadow map and we want to actually calculate the correct depth from the point of view of the camera versus the point of view of the light, we have to remember in Vulkan to put it into a different range, or rather in OpenGL to put it to a different range than when we're dealing with Vulkan. So that's an example of a real world kind of use of why we might want to actually have different calculations. You can obviously have, if you wanted to, like some kind of uniform, and that would be like the modifier. You know, I like doing it more in the GLSL code because it makes a little bit more sense, I think. And you don't need to like use up a uniform slot or anything. Okay, anyway, so let's take a look at, this is again becoming a huge video, but we haven't had a Game Engine series episode in a while, so I hope you guys are enjoying this. The next step is going to be probably to look at what actually happens in the shader. So as I mentioned, the shader, this is a bit annoying, but whatever, all these inconsistent line endings. The shader actually has like had the most changes, I think. Like if you look at this diff, you know, this is all the stuff that's changed. Basically everything, the whole file has pretty much changed. I've basically rewritten it. It also used to be like 187 lines, now it's like 374. So it's been expanded, it's been rewritten. What happens now? Well, again, as you saw, the API stays the same. This part did not change. This whole idea of like, you know, we're creating a texture shader with this GLSL code, that doesn't change. We don't really need to be doing this, by the way. I haven't actually even tested this with textures. This doesn't need to be done anymore. In fact, I can just get rid of this. This isn't like 100% done. Let's just see if this works, because we are actually using the white texture as texture slot 0. So there you go. See, I still am writing code in front of you guys. That will never change, I guess. Or rather, deleting code. Pink cube. Okay, that does still work. So if it wasn't a white texture, we probably wouldn't see anything if the texture wasn't working, because it multiplies the color with the texture. And if it was missing, most likely we'd have black and we just would not show up, or it will be black. Anyway, so this doesn't change, right? So what actually happens is we still obviously support that. We take in a file path. And then the first thing we actually do is we create the cache directory if needed. So as I mentioned, it's very slow for us to recompile all of these text shaders every time we run Hazel. That's not needed, right? Every time the shader changes, we do need to do that. And at the moment, we're not detecting changes. We're basically just saying, hey, does the cache exist? If yes, use the cached binary file. So this is us creating that cache directory, right? Just to make sure this doesn't need to be here. There used to be 2, now there's 1. So the cache directory is going to be assets, cache, shader, OpenGL. And again, for future APIs, we might have like, Vulkan here, whatever. At the moment, it's just OpenGL. Make sure assets directory is valid. Apparently it's, to make sure that the assets directory is actually assets, because it might not be in the future. Then we just see if it exists. And then if not, we can use the brilliant C++17 file system API to create recursively all the directories along the way to make this path happen, which is amazing. I love that. So that's what this does, just to make sure it's there, because if we try and write a file and the directory doesn't exist, it won't be able to. Then we read the source and we pre-process it, which means we split it up into the different source codes, because as you know, we still have this type vertex, type fragment of the whole Cherno shading language situation. So that's what that does. That has not changed. Now I actually hooked this up with a timer to see how long it takes, but basically these are the 3 steps. Compile or get Vulkan binaries. That takes in the shader sources, which is the actual string source code for each OpenGL type, right? So again, we have, like a vertex shader, a fragment shader, that's what the type is. We create a shader seed compiler. We look at the, we set the options. In this case, what we're doing is we're just setting the options to basically be Vulkan 1.2. So we're compiling for Vulkan 1.2, as I mentioned, right? In this options, it would be a fantastic place to actually add a macro definition, like I mentioned, of OpenGL, right? So you can just be like, we're defining OpenGL, and you would have to do that for the Vulkan version here, because as I mentioned, the preprocessor is going to run, you're going to lose all your text. So you have to do it there. Optimization, you can set to false. I don't know why we would ever not optimize in this case, but whatever. And then we set it to performance, just a little flag here. Could be based on some input parameters, whatever. Then we just get the cache directory and we basically compile all of the different shader sources. Ignoring the cache, we basically create a module here and we just do compiler.compile GLSL to SPIR-V. We just pass in our arguments, basically. I don't think anything here is useful. We have our stage. We just convert that into shader C. So vertex shader becomes shader C, GLSL vertex shader, fragment shader becomes that. Pretty simple stuff. If the compilation doesn't succeed, we print the error message as usual. And then we actually have the shader data inside a vector of words. It likes to use the UN32Ts instead of bytes here. And then we write it out using the output stream. Someone convinced me to use the C++ API instead of file. I think in Hazel Dev, it's just file and fopen, because that's how I roll, but I guess we'll be C++17, C++y here, and we'll do this. I think it mostly just wraps. I think this mostly just wraps the API anyway, and I've lost it. Maybe not here, but I'm pretty sure it does. Probably not worth me doing this now, but you might have to take my word for it. Basic OF stream, basic O stream. The hardest part is just trying to find all of this stuff, to be honest, especially when you're rushing. No, okay, whatever. It's definitely got some more like validation and safety stuff around it. Okay, so then we've got, so once we have created that, we cache it to disk, right? And that's what this branch over here does. If the cache exists, we read it, we open it, and we now have our data. If not, we compile it and we still have our data, so it gets written. And then once we have all the shader stages done and compiled, which is what this code does, we can reflect on it. So what does that do? I keep trying to build. So what reflection does at the moment is mostly just printing stuff. We don't actually use the reflection yet. We will in the future for materials, just to see what's available and potentially for validation as well. But what this does at the moment is it's just a demonstration of how this whole reflection works. So you can see OpenGL shader reflect, and we actually print, with the file path, the shader stage to string. That just basically, converts that to a string. How many uniform buffers do we have? And you can see we can use the SPIR-V cross API here. Once we've reflected over it, compiler get shader resources to actually see how many uniform buffers it has, how many sampled images it has, so like textures, right? What are the uniform buffers? What are the names of the uniform buffers? How big are they? We can actually even iterate through the members if we want. What's the binding set to, right? Is it 0? Is it 1? We can see all of that stuff here. And this is just a little example to show you guys how the reflection works. So the way I write this code as well is I try and almost explain it in the code itself. So again, you should now be able to hopefully look at this reflect function and be like, this is how I can find out potentially the information that I need, and then write that code in my own engine. So I'm trying to be extra kind of verbose descriptive with my code. I'm not trying to be all, for int x equals y, w is less than z, cryptic stuff. This is supposed to be very easy to read, hopefully. That's my goal with this code anyway. And of course, these explanations, hopefully, if you can be bothered sitting through 40 minutes, I better not be running out of disk space, because that would be the worst. No, I'm still good. Okay, so where were we? Yeah, that's this stage. Then we do the compiler get OpenGL binaries. So what does that do? Well, the same thing, but so we have the Vulkan binaries now. We have them. We've either loaded them from disk and done reflection on them. I should really move reflect out of the compile function. Don't know why it's here. We'll do that later. We already have the Vulkan ones. We've either actually compiled them and then written them to disk, or we've read them from disk. So now what do we do? To do read from cache. I think we already do that. It's probably done. Compile what? I don't know. I'm getting rid of that. So we have this is just, I think, the where it goes. But basically, what does this do? Same thing, except in this case, right? Where does the cross compilation happen? I don't think we've done that. Or does it happen here? Yeah, it probably happens. Yeah, it happens here. Okay, so this time though, we create a new compiler and we set it to be OpenGL and OpenGL 4.5 instead of Vulkan 1.2. And I think 4.5 is the latest, by the way. So there's no 4.6. Currently, no difference between OpenGL 4.5 and 4.6. So there you go. And GLSL Lang doesn't accept an OpenGL client of 460. Okay. That's why our shaders as well are obviously 450 core. Stop telling me about this. I should have... Okay, whatever. So we go through the Vulkan SPIR-V. We either read the binary if it's already on the disk, right? So this is, by the way, as we're going through the Vulkan SPIR-V, this is us reading the GL shader stage cache OpenGL file extension. This is us reading not the Vulkan stuff. We've already got that. That's what the Vulkan stage was for. This is us trying to read the OpenGL cached binary if we have one. If we don't, we go over here. So if we don't, we cross compile. We take in the Vulkan SPIR-V, which comes from here. We're going through the Vulkan SPIR-V, even though we're trying to retrieve the OpenGL SPIR-V. We're going through the Vulkan SPIR-V, and then we're cross compiling it into OpenGL. And how do we do that? We do a compiler GLSL. And then I think by default, this will just be set to be like an OpenGL compatible one, I believe. I think, yeah, so version 450 and Vulkan semantics is false by default, right? So it's not going to use Vulkan GLSL features. It's going to use GL compatible features because it's false. And there's a few other things you can do here, actually. Which is really useful. I haven't looked at this too much because we have a pretty simple example. I think some of these might be used in Hazel Dev specifically. But we basically compile that source code. It gets saved into OpenGL source code. So we have these two things. We have OpenGL source code. We save that just so we can, for debug reasons, view what the cross compiler generated, what text it generated. But otherwise, you can see we have our Vulkan and OpenGL SPIR-V. We also, at the moment, retain all of this in memory. You don't need this in memory once you've reflected and once you've compiled and sent it to the, to OpenGL, but we still keep it for now just for debugging purposes. Yeah, we compile that. Yeah, so we've cross-compiled it. We now have the text, and then we send the text into GLSL just like we did originally with our original text, but for Vulkan. Right, so hopefully all of this is making sense. Read through the code, and you can run it with a breakpoint and with debugger. That might help as well. And then we cache it to disk. So what does that mean? That means that as you saw me run that, first of all, let's take a look at this. The assets directory has a cache directory, right? And inside the cache directory, there's a shader directory, OpenGL, like you saw, and then we have 4 files. We have the opengl.vert.frag and we have the vulkan.vert.frag, right? If I delete these, or in fact, we can test it by just deleting the whole cache directory, right? It will have to recompile all of them from text. And at the moment, because we're not detecting changes by like hashing the string or whatever, hashing the binary, that's the only way. If you change your shader, you have to delete the cached one. Or maybe I'll set it like in HazelDev, there's a force compile flag that you can give. Anyway, as you saw, that took, wow, 6.8 seconds. Usually it takes about 5 seconds. I don't know why it's suddenly slower, but that's how long it takes to compile everything. Now, and you can see that we've got uniform buffers, and the reflection has worked here as well. We have one uniform buffer. It doesn't have a name. I didn't actually give it a name, as you know. I was just using, I didn't give it a name. The name would go here, right? So it's generated its own name. But we know that, look, it's got a matrix called view projection in it. That's what we see here. We have size 64. Binding 0, 1 member, right? So we can get access to that. We could print the names as well. It is trying to print the name of the uniform buffer. It's had to make one because we haven't given it one. But anyway, 6.8 seconds. That's how long it took to launch and to compile all of this. Now watch how long it takes if I run it again. Instant, right? 19 milliseconds, right? Huge difference, 6.8 seconds, 19 milliseconds, right? So that's why it's so important to cache your shaders. We don't want to, spend a lot of time compiling shaders. And then you can open up your pink cube, and everything's great. That's basically the major system. Again, I haven't talked about uniform buffers, but that's what we do now with our shaders. We compile them using that. Now the final stage, which I didn't touch on, was the creating the program. And I apologize for this hugely long video. Maybe I'll break them up in the future a bit more. I just didn't think I would be able to talk so much about this stuff. But anyway, I hope this level of depth though is good, because I know that a lot of people did still want it to be very in depth. We create the program the same way, and then we just go through all of the stages, right? And we get inside the OpenGL SPIR-V, and then what do? GL shader binary. Right, we just say binary format SPIR-V. This is obviously the OpenGL SPIR-V, not the Vulkan SPIR-V. We do GL specialized shader that just points it to the main function. There's a few other things here like specialization constants and stuff like that, but the entry point is the important one that we need to give. We're not using actual specializations. Then we attach it to the program. We link the program as before. This part is identical to before. And then we just link it and do all of that stuff. Delete the shader IDs, detach the shader. Delete them if they fail. I think we also should delete the shaders here. Let's just try that. Let's detach and then delete. We can obviously group those two for loops together, but I'm just curious if this works. I assume so. I think this is what we were doing before. The program can't be deleted, but these individual shader objects should be, I think. So let's do detach and delete like that. And we've saved ourselves a comment. We can get rid of that comment. Brilliant. So yeah, and then this part, as I mentioned, that remains the same. So not much has not like everything has changed. It's still kind of the input and output of this class is identical, right? It's just the actual the contents of it has changed. We still have all of these uniforms. We can keep them like these functions, but again, they're going to be very OpenGL specific, so we'll probably end up getting rid of them eventually. But that is basically currently how the shader system works. I don't want to go through, there's a few different things I want to go through. I will commit all this code so you guys can take a look at it. I have a lot of other stuff to talk about. I just did not realize, as I mentioned, this would be so long. But yeah, I think there's also so another huge thing that I want to talk about, which I'll talk about in the next video actually, is our whole dependency on the Vulkan SDK. So this uses the Vulkan SDK. Vulkan actually ships with all these tools to be able to compile this stuff, and which is great. The Vulkan SDK has two types of libraries. We could compile it ourselves. Well, some of these libraries ourselves. I don't really want to. I think that it might be something that we might have to do in the future for like different platforms. But for now, for Windows, there are precompiled binaries. Now, these precompiled binaries are very big. And obviously, we need debug binaries and release binaries. The debug binaries are 2.5 gigabytes. I don't want to commit them into the project. That will massively inflate our Git repository size. So instead, you have to download them basically from Kronos. But I've written some scripts to do that, and that's what we'll talk about next time. So anyway, I hope you guys enjoyed this video. If you did, please don't forget to hit the like button. Patreon.com/thecherno, best way to help support everything that I'm doing here. 50 minutes I've been recording for. I don't know what the edited video will be like, probably very close to that. Let me know what you thought of this kind of new format. You can kind of see, I hope, that the fact that this has taken 50 minutes to explain, this took me like, I don't know how many hours of actual work, maybe 4 or 5 hours of actual work. I have done this stuff before, and Hazel Dev does very similar stuff as well. But it was live streamed, so you can catch the live streams, or you can go through the backlog on Patreon as well and take a look at that. I've labeled them like Game Engine series live stream or whatever, so you should be able to find them. But you can see how, hopefully, how if I had actually done this for the first time or whatever, or written all the code in front of you, it would have taken a lot longer, and I don't think it would have been worth it, because I personally think this kind of reflection way of doing things is hopefully going to be more useful to more people. But anyway, leave your thoughts in the comment section below, please. Thank you all for your support, and I'll see you next time. Have a good day.